material. So over the past several weeks, we're already on week 5. I know time's been flying, but I'm sure it could also seem like you've been here for a year already. But I just want to talk about where we went and now where we're going. So the first couple of weeks, week 2, week 3, we learned OOP and Python. Well, what the hell just happened? OOP and Python. Last week, week 4, we talked about HTML, CSS, JavaScript, Bootstrap, and we were building like front end vanilla like web applications. Week 5, we're doing SQL now, and we'll cover what SQL is and Postgres right here. And then next week we're going to jump into the Django ORM. If you don't know what that is right now, don't worry about it. But this kind of links, like SQL kind of is related to the Django ORM. So this week we're just going to be covering SQL and Postgres. So yeah. So just quickly review of this week's weekly README, what we're going to cover: SQL, database schema design. We're going to have assessment 3 at the end of this week. Just kind of why is it important? Every application out there utilizes a database. The most commonly used database is a SQL database. We'll cover what that is. So what you'll be able to accomplish, you'll be able to create databases via the command line, create database schemas, the associations between the different tables, create, read, update, delete from a database, query data, and design database schema for different applications, as well as modify. And also you use Python to execute SQL commands. Any questions about kind of what we're going to be covering this week? No. All right, let's talk about SQL. So, Code Platoon, we cover, JavaScript, Python, Django, React, but there's a plethora of different languages out there. Just so happens that, JavaScript and React are super popular right now, and Python is, I think the most popular coding language right now. But over the past, 10, 20 years, there's been a bunch of different languages that have been popular at a given time. Like specifically here in Chicago, Ruby was super popular in the late 2000s and early 2010s. However, Ruby's drastically declined in popularity, and with the rise of Python and other object-oriented programming languages. However, one thing that won't most likely change in your career is SQL. SQL's been around since I think the late 70s, early 80s. And it really, it's definitely changed, but it is the one thing that's probably going to be constant throughout your career. Whereas you'll learn a bunch of different programming languages, front-end languages, back-end languages. However, SQL, more likely than not, will not change throughout your entire career. So with that, over the past couple of weeks, we've just been writing programs, and we haven't really been storing a whole lot of data. We have been using CSV files. However, working with CSV files, as we've kind of discovered last week, hasn't been the easiest. You'd have to store each SQL record in like a class object, store that into an array. And anytime we wanted to read and write to a SQL, to a CSV file, we'd almost have to rewrite the entire CSV file. But now we're going to be full stack developers. There's another mechanism of how we store that data, or just store data in general. And can anybody tell me where else would we store data if it's not in a CSV file, if it's not in a text file or a JSON file or an XML file?
A database?
A database. Awesome. So SQL is, let's go in here. There's 2 types of databases. There's relational databases and non-relational databases. SQL is structured query language for relational databases. So a relational database consists of tables, and those tables are related to one another, and you can create your database for each table to be related to one another. That's why it's called a relational database. So here's just a visual representation of a database that consists of multiple tables. So here's products, customers, orders, and order status, and how they're related to one another with these lines. This is just a visual representation. And there's also non-relational databases. And non-relational databases are kind of like the opposite of relational databases. The data the way it's stored within the database, it's not related to one another. So you have to come up with creative ways to relate that data to one another. And there are benefits to relational databases, as well as there's benefits to non-relational databases. But relational databases are the most popular. You will be working with relational databases at some point in your future. There was a period of time where non-relational databases got really popular. And then, developers and engineers realized, relational databases still, the benefits of using relational databases for whatever problems they're trying to solve kind of outweighed the use of non-relational databases. So relational databases are still the most popular type of databases to use when building out applications. All right, let me move this. All right, so RDBMS is a horrible acronym for Relationship Database Management System. So RDBMS just stands for Relational Database Management System. So there are two halves to RDBMSs. There's the storage mechanism, which is essentially how the data is structured and stored within the database. And that consists of, tables, columns, and rows. So if you think of like the CSV files or like an Excel file or a Google Sheet, like an individual sheet would be considered like a table, and that table has a columns and rows of where you store that data. So that's just kind of like if you envision a relational database, kind of like an Excel spreadsheet, just like from like a visual standpoint. As well as the second half is how you actually query and extract data, insert data into the database. And we use that using structured query language, SQL or SQL. Any questions about relational databases and SQL so far? All right. So we kind of talked about the storage mechanism consists of tables, columns, and rows. So here is an example of a table, and this table's name is called students. So there's a best practice of how you name your tables. So this is called a students table. It should consist of a noun and it should be plural. So this students table will store a bunch of students. So it'll always store plural students. And this is kind of like a visual representation of a student's table. Notice how it has some columns and it has some rows, or column headers, rows. So again, that big thing is called a table. And tables consist of columns such as ID, first name, last name, on probation. And each table also consists of a row, which stores an individual record in the student's table. So for example, Tiana Lowe is with an ID of 1, on probation is false. This is an individual record within a table. Any questions about kind of like the visual representation of what a table looks like.
I have a question.
Yep.
So I'm like super confused as to SQL is just a way to access information from data tables, right? From a database.
Correct.
Okay, and we're going to be using Postgres.
Yes. So,
Okay,
yeah.
so is SQL only used to access information from Postgres and nothing else?
No, and we'll get to that. So SQL is the language to get data from a relational database. And there are a bunch of different types of relational databases, which we'll get to.
But the biggest and most popular is Postgres.
It is very popular right now. I don't know. I'm pretty sure it's the most popular database. So Postgres is a relational database that we're using, and Postgres is an open source relational database. That's why it's so popular. It's open source, but there's a bunch of different ones, which we'll kind of show you, like, MySQL, Oracle has one, MariaDB. There's dozens upon dozens of relational database management systems that use SQL to extract data from.
Okay, but we're mostly just going to use SQL to deal with Postgres. That's it.
Yes, so we're going to be using SQL for our Postgres database. And that's why SQL more likely will never change, because there's all these different relational database systems out there: Postgres, MySQL, Oracle, Microsoft SQL, or MariaDB. There's all these other databases out there, but the core to those databases, they use SQL, structured query language, to execute queries on those databases. So the language doesn't change. The database management system might change, but for what we're using, we're going to be using Postgres. All right. So a schema, you're going to hear this term schema, which is a blueprint or a representation of a plan of how we're going to store our data in the database. So a schema, so if I go back here, like this right here, that consists of multiple tables: product, order line, customer, orders, order status, followed by all this other information. This would be considered like a database schema, because it consists of multiple tables, multiple, So a schema is the plan or design or blueprint of how we're going to store our data in our Postgres database. So primarily focused on describing three things: the table names, the column names, as well as the column types. And we'll get into the column names and types shortly. Other parts of the schema include specific values of what type of data goes into the columns. So like here, we have ID as an integer, first name is probably a string or varchar or a text field. On probation looks like it's a Boolean value, true or false. So we might constrain our column types to what type of data can go into each column. And we can also add checks on there to make sure that when data is entered in here, make sure it's unique. Maybe it is a Boolean value, or it's not null, or give it even a default value if we need to. So we can include a value not null versus null, foreign keys, indexes, and a bunch of other things, which we'll kind of cover. So tables are identified by a name. So right here is a short snippet of an actual SQL query. So create table students, and then when you're naming tables, they should be nouns, plural, and all lowercase. And they should also be like snake case as well. So if you think of Python as snake case, everything's lowercase. That should also be how your tables are made. So for example, students should display a list of students or a bunch of students. Create table addresses will store a bunch of addresses in that table. It says also include a unique integer column named ID on every table you create. So if you look here, every table or the students table has an ID with 1, 2, 3, 4, 5, and each ID is unique. So you'll never have more than one of the same ID. So there'll never be an ID two, there'll never be multiple IDs of 2 within the students table. And more often than not, this ID field and this ID column and the ID value is automatically generated for you because it's so common that you would always have an ID column on your table. Questions about tables? All right.
Did you say that the IDs are often automatically created for us?
Yes.
Is there certain scenarios when it would not be automatically created? And like, how do we know if it's going to be automatically created or not?
Yep. It's when you define, when you're creating your schema. So when you're actually creating the query to create your table, you'll write a specific query in there to make sure that each one of these are unique. And then it'll automatically generate for you.
So it's not necessarily going to be the case where I create a table that just has, you know, names and ages and, you know, randomly it also creates unique IDs. I think what I'm hearing you say is if I create a column of ID, then SQL will automatically assign new values to each entry. Is that right?
Yes, but you'll have to actually define the column ID and put like another query to actually make it ensure that that is it's called a primary key, and we'll get to, but it'll automatically make sure that this ID is automatically generated for you.
Okay, awesome. Thank you.
All right. So here are some examples of table names and what they would store. So if I want to store a bunch of people or users or like people, it would be like a person's table, or it can be a user's table, which is very common. Purchase orders, it'd be purchase underscore orders, pretty self-explanatory. If I'm in Facebook or, you know, LinkedIn and I want like a post, I'd have a table called likes or impressions. If I can store multiple different types of impressions like likes, hearts, thumbs down, thumbs up, something like that. So it'd be like likes or impressions. So always be plural, always be lowercase and snake case as well, if it's multiple words. All right, let's talk about columns. So each column has a name, have it be lowercase and singular nouns or adjectives. So for example, students will have an ID field, a first name field, last name, and on probation. So the field name or the column name, ID, first name, last name. So just like this, ID, first name, last name, on probation. So this is a SQL query. So I'm creating a table called students, and now I'm adding columns to it. The column name is ID, first name, last name, on probation. Questions about the column names? Again, they should be lowercase, snake case, and singular.
So I don't know if it's too early to ask, but where are we actually doing this? Like, are we creating a .SQL file or?
Yep, you can do it, and we'll walk through it. So yeah, you'll be actually creating a specific SQL file, or you can do it directly in your SQL database in the command line. in the terminal, but we'll do both. So we've got column names, ID, first name, last name, on probation. Now we want to store what type of data is stored in each column. So for example, the ID is going to be an integer. The first name is probably going to be a string or text, or also known as a varchar, which stands for variable character. And what's here in the parentheses is how long that string or text field or the varchar, how many characters can be stored in the first name. So for example, this is 255. Last name, varchar, 255 characters. So that's the max length that this last name field, that's the max number of characters that that last name field can hold. If it's anything more than 255, so 255 is the max. You can't do 256 or else it's going to throw an error. If you wanted to store more, like if you're writing an essay or the about me section or something like that in your LinkedIn, that field is probably going to be a text field that's anything longer than 255 characters. And the reason why it's 205 characters is the max length for a varchar is because that's the max number of characters that can be stored as in 8 bits, an 8-bit integer. Anything else you can store text field that's up to like 16 kilobytes or something. So varchar is a fancy way of saying a string up to 255 characters long. Now you can store less than that. You can do varchar 100 if you want, or varchar 50. It just depends on what you want to limit the user. Essentially, yeah, what you want to limit the data that is stored in the first name field. So if you don't think there's going to be a first name that's over 100 characters long ever, if you don't want to ever store a first name that's over 100 characters long, you can just do varchar 100. Question about the types. And there's more types than this. There's integer, varchar, text field, date, time, and we'll get to that in a second. So again, we're currently going to be using Postgres, which is a relational database management system. And we're going to be using SQL to run queries on that database, on our Postgres database. But there are a bunch of different types of SQL databases or relational databases like MySQL, Microsoft SQL, Oracle, MariaDB. There's a bunch of different types of relational databases that utilize SQL. But when it comes to types, integer, varchar, Boolean, they all pretty much use the same types for their fields. Integer, decimal, varchar, text, date, timestamp. There's other ones, but these are the most common used. So if you know these types, you'll be able to more often than not, if you know how to use Postgres, you'll more often than not know how to use MySQL, Oracle. It's just a different type of flavor of a relational database or a SQL database. Questions about the column types?
Yeah, Tom, quick question. If you're, say, for example, storing media, like media files, are you actually just storing a file name, like a directory name in these variables to like some non-structured data source then? Is that what's happening?
That is one way you can store file types, is like the location of where that file is located in some other storage system. Yep. So if you look at, so if I go to Google and type in like Halloween pictures like that, and if I like, I don't know what's going on there. If I like right click, copy image address, somewhere in this database, it might store a link to where this photo is located at. And that this link is probably, it could be an AWS S3 storage bucket or something like that. So it could store a direct link to it.
Thank you.
All right. So schema modifications. So just like you would do pseudocode when you're creating, you know, a class or some program, it's best to really plan out your schema design of whatever application you're doing early and try to think of all the different scenarios you might use your application for. So if you think of like Amazon, when Amazon first came out, and I think it was like 94 or 95, all they did was sell books. And they might have had like a books table that just stored a bunch of titles of books. But as the Amazon continued to grow, they started to sell, you know, DVDs, all kinds of different products, their application. So early on, like their database might have just been like books, users, accounts, and purchase orders, or like something like that. But as Amazon grew and sold more than just books, and like started selling DVDs and everything, they might have to like name their books table to like inventory, and then also add different tables to like for like Amazon Alexa and, you know, Dropshift. They're like their sellers and all kinds of databases that they had, or all kinds of tables, and maybe they had to add columns to tables because maybe first the users you can only ship to one address. Their users can only ship to one address, but maybe their users had two addresses they wanted to ship to, so they had to like adjust their database to allow users to store multiple addresses for their accounts. So when making schema modifications, so as you maintain software, it's expected that you'll create new classes, write new methods, and refactor existing code. You'll do the same to your database schema. So you'll be adding tables, adding columns, changing different column types. So when you're modifying your schema to an already existing database, it's not cheap. So as your database grows, you have to be very conscious of how you're going to change and modify your schema, as well as modify the data within your database. So changing your schema early on when your application is small is not that cumbersome, but as your database grows, making changes to your database can get really expensive. And just be cognizant of when you are designing your database schema, when you're like designing like this, make sure you try to think of, all right, as this thing grows, what else will I need? So when you initially design it, it's scalable. So you don't have to make a lot of database or schema modifications. So you don't have to make a lot of modifications to your database as it scales, or as it grows, or as your application grows and adds new features. All right. So changing a database schema isn't cheap. It can often require coordination with code changes and or other tools, third-party analytics tool, or an Excel formula to run against a CSV export of a database table. So just want to reiterate, take your time when designing a database. You'll often be stuck your schema choices for some time. So you can't just automatically change your database schema as your database grows. So if you're convinced you wish you had a different schema, the time to make the change is now. So the earlier, the better. So making the change will never be cheaper than today. Any questions?
Tom, would it make sense to, like, say initially I think that I only need, three columns or whatever. Would it make sense to put in an additional, 7 and just label them as, for future potential use, 1 through 7?
No, because then you're just storing empty data, or you're having a bunch of not null columns or null data, and that's expensive too. So yeah, definitely don't just make your column have empty columns just for the sake of the off chance you're going to have additional columns in there in the future. So that's why I just plan accordingly. And then once you do grow, and if you designed your schema correctly or like most optimal at that time, adding changes or making schema modifications won't be as cumbersome or as dirty as if you just didn't plan for any changes. And we'll get to that in the future. So single responsibility. Single responsibility. Just like we try to write single responsibility code, we also want our database schema to have our tables be single responsibility. So as software developers, you try to avoid big classes, long methods, and long lines. We've learned that smaller is always better when it comes to software. The same thing goes with our tables as well. So an individual table should really only have one type of data. So for example, in this table, we have first name, last name, on probation, line 1, line 2, city, state, zip code. What types of data are we storing in this table?
A person and an address.
So we're storing a person and an address. So where do you think we can possibly break up this table into 2 separate tables?
The address portion.
Yep. So maybe create a break right there and have a students table and an addresses table. So when I'm querying the table, the database, if I just want to grab the user, I don't ultimately grab this entire, essentially all this other data that I don't need. I'm not grabbing the address that I don't need. So I can create 2 separate tables. So I've got the students tables and I've got this addresses table. But now notice how I've got in the students table, I've got the first name, last name. And down here in the addresses, I also have a first name and last name that's associated with this table or with the addresses table. So again, you don't want to repeat yourself. You don't want to have duplicate code. You don't even want to have duplicate data in your database. So for example, first name, last name, Tiana is also here. What if Tiana, gets married or something like that, or adopts a different first name or last name, or their parents get divorced or something like that, and Tiana changes her last name. So I'd have to update the students table as well. So first I update the students table. So Tiana changes her last name to Low to Love or something. But now I'd also have to update the addresses table last name, Tiana Love. So if I had to update her last name. So here comes a problem. So I'd have to update 2 records for 1 change. Is there another way I can do this? Is there a way I can represent Tiana's address by removing the first name and last name?
Is this why you give them the ID number? Because you could do it that way?
I can use the ID number. And what do you mean by that?
Like give them, rather than mentioning the name again, use that record's ID number from the student tables as the ID number in the addresses table.
So use the student's ID. So like Tiana 1 in place of the first name and last name here.
Her address record would also be ID number 1.
So ID 1 here and ID 1 here.
Yeah.
So so each record would, so every time I create an address in here, it would just automatically create an ID automatically. So you are kind of on the right track. So I create a relationship, but I could add the student ID. Maybe I created a new header or new column of student underscore ID and had that student underscore ID value be 1 here. But what if I had 2 students that lived at the same address? So I've got,
We could absolutely put, and Susan, you were really right, very close. If we put an address ID on students, then each one would be, you know, let's say Tiana Lowe is 4, Elvis Snipes is 5. And then if they happen to get married, or yeah, if they get married, then they move in with each other, and all I have to do is update one ID on one student, point to the new address. And then anytime I want to say, hey, what's this student's address? I would just look up that ID. And now I have all their address information.
yep, exactly. So I can make a modification to my students table, add an addresses ID column, and that address, the value of the address ID is the primary ID, or the ID of the address in the addresses table. So Tiana Lowe has an address ID of 4. I can look at the addresses table, see what address is at the ID of 4, and now I can see that Tiana lives at 381 Maple Street. And if all of a sudden Tiana decides to move in to Rogers Boulevard, all I'd have to do is update the address ID in the students table to number 5. And now I can see that Tiana lives at, 8917 East Rogers Boulevard. Michael.
Do you typically try and make the least changed or the less often changed portion of your database kind of your base that you point things back to, and then the other parts that get updated, do you point back to that? How do you know to point, from addresses to students versus pointing from students to addresses?
Yeah, it's good. That's the type of relationship that, so addresses belongs to students. So in this specific table, this is a one-to-many relationship. So an address can belong to many students. So what if Tiana had a sibling? So Tiana had a sibling called, say I was Tiana's sibling, it would be Tom Preet, that also lives at the address of 4. So that's why we're having the address ID column on the students table, because multiple students can live at the same address. If we had it the opposite way, if we had like student underscore ID here, that means only one student would be able to live at the 381 Maple Street, because you can't store multiple integers in a column.
Okay.
Outside of this one example, well, it works for this one example. I just don't know if it only works. Could we just use like sentence structure? Like students have addresses, but addresses don't have students. And that's why the students would link to the addresses.
Students have addresses and addresses don't have students.
Correct. So in terms of just like possession, it's like students would have an address, so we'd link to it.
Yeah, I guess that works. Yeah.
But would it work with everything, or does it just work for this and I just created that statement?
It would work for this specific address or this specific scenario, but it would work for other ones as well. This is like a one-to-many relationship. So any one-to-many relationship, your sentence structure would work. All right.
Tom, I have a question.
Yep.
How does it know, for instance, the address ID field? How does it know that it's not just a number 4 and that it relates to the ID in the addresses table?
That's a good question. So when we're designing or when we're actually writing the SQL query to create this students table, when we create the address ID field, our query will actually say, look at the addresses table. This is called a foreign key specifically. This address ID is called a foreign key. And that foreign key needs another table to relate to when and that table is going to be the addresses table. And there's several different ways we can do that when we're actually writing our SQL. But yeah, there's a couple of ways. Yeah, there's several ways we can do that when we're actually writing our SQL. So yeah, again, when we're defining our tables we're writing actual SQL, we're gonna specifically say the address ID column is a foreign key or is gonna reference the addresses table. Yeah, good question. Also, you see these things called primary keys. The IDs, the first column, this is considered a primary key. So when you hear that word primary key, that's what the ID is referencing. So schema design or data integrity, good schema design improves your data integrity. So careful use of database constraints such as column uniqueness or not null will protect you from situations like this. So have you ever tried to sign up for a different application? You type in a username, it says like that username already exists in that database. That's because when you're signing up and click enter, it's doing a uniqueness check on the email field, for example, saying, hey, your username already exists, so you can't use that username. So in an example like this, if you don't have a not null or a uniqueness constraint on your email field, you can technically type in you can store two emails of the same name or of the same email addresses. So when James goes to log in for the first time or second time, it's going to look through the database, looks for an email address called james@example.com. And when they type in the password, how is the application going to know what password to look at? It's not going to know. It might just pick a random entry and use that password. So when designing your database for each column, you can make sure, it depends on the constraint of what you want your application to do. But for an example, an email field, you might want to have only unique emails stored in there. So you can't have duplicates. Any questions about making sure when you're storing data in there, if it's like a password or a username, you only want to store one username of that value in the database. And when you're designing your database schema, when you're actually writing this, in addition to varchar, you can add other attributes after varchar to say, hey, make sure that this first name is unique or this email is unique, make sure it's not null, or give it a default value. Questions?
I got a question. In that example right there, wouldn't it always still default to the first one though? I mean, you shouldn't store multiple emails, but wouldn't it query in order? Wouldn't it always get the first password?
I don't know, but I wouldn't assume it will always grab the first one. So I wouldn't assume it always grabs the first one. I don't think it does. I think it just, whichever one is the first one to come up. Because it doesn't loop through when it searches. It doesn't start at 1, 2, 3. There's a specific data structure of how fast it searches. So it can start from the back and front and search, and it uses a different data structure to search through it.
So it wouldn't be deterministic. So, I mean, we could have random, it could pop out a random email.
Yep.
Yeah.
So if it was stored like this, for example, anytime you log in, it could randomly choose whichever one you, it would select either or. It's like, it would be random. Somebody else have something to say? All right. We see this password here. Has anybody ever seen a password like that before? Does anybody even have a password like that? Does anybody know what this is?
Is that a Google Drive one? Hash of a
Yep.
password.
Yep, this is a hash password.
Try with
So
some salt.
in databases, you never want to store passwords as plain text because you don't want your employees to see all your users' passwords. Or if your password or if your database gets hacked, which I'm sure you've all heard of stories of big companies getting their database hacked and all of a sudden all their users have been compromised. This is what a hashed password is. It means it goes through some sort of hashing algorithm, some type of, remember Caesar cipher where we cipher, it's like scramble up your specific text or anything. This is what this is kind of doing, but on like steroids. And it's also probably salted as well. But yeah, so you never want to store passwords in plain text. It goes through a hashing algorithm. And most applications already have some of this already built into it. Like Django already has it, all that. All right, let's talk about some SQL queries, actually writing commands in SQL that will actually be executing to do various things on a database. So the command, the query create table, which we've seen in the past, is a SQL query to create a table. And the most, when you're actually querying a SQL database, the biggest ones you'll see are select, insert, update, delete. So select is you're going to retrieve rows that match a specific query. Insert, you're to insert new data into a database. Update, you're updating or changing data that matches a specific query. And delete, you're going to delete rows that match a query. So select, and we'll go through this after the break, but select. So by far the most common query. So select allows you to retrieve matching rows from the database. So back from that students table, like so, if I wanted to select all the students from the students table, I can do select star, and that's like what is it called? A default to like selecting all the columns in the table. So I'm selecting everything from the students table, and you'll return ID, first name, last name. So select everything from the students table, which will return all the students. And now you can also specify what columns you want from the students table. So select ID, comma, first name from the students table. So select ID, first name from the students table. If you wanted to select a specific student that matches a specific condition, so for example, I just want to grab the student that has an ID of 2. So select ID, first name from students, where is another query argument, where ID equals 2, and that will return ELDA. So there are other conditions, these other where conditions. So like where ID equals 2, you can do ID equals a value, does not equal a value, like bang equals, or the 2 angle brackets. You can do greater than or equal to, less than or equal to, between 2 values. So where ID is between 5 and 10. In, so in represents in a list of values, and like is also common, that matches a string with wildcards. So maybe like, we'll kind of show you. So select everything from the students table where first name equals Andre. So that's the equal sign. Select everything from the enrollments table. So maybe there's a table enrollments where the student's grade does not equal an A. Select everything from a classes table where the credits, so there's probably a column with credits, are between 3 and 4. So those are also common keywords, between and. Select everything from the enrollment table where grade is in an A or B. And here's that like. Select everything from the classes table where the name like with this string of art with this percent sign. So this percent sign, this means that select all the classes that start with the word art and then have some other values after it. So the like that starts with a class that starts with an art and has credits greater than 3. So you can add conditions to each other. And we'll go through some of this. Any questions?
Hey, Tom, is I don't know if you mentioned this, is between, is that inclusive?
It is inclusive. So between 3 and 4 will include 3 and 4.
Is
Here and not between, like everything except for 3 to 4, where it's outside of.
I am not sure. That's a good question. I can say not between SQL. Where, yep, it looks like that does work. W3 schools, so not between does work as well. I heard another question.
what's the difference between the percent and the star?
So the star is just a, I forgot what it's called, where to go? It's just a short operator for everything.
Wildcard?
Wildcard for everything. So select everything from the students table. So select all the columns from the students table. The percent side is also kind of like a wildcard, but it just says like, hey, anything, there could be values that come after that as well. So anything that starts with art and then that has also characters after art. That kind of help answer your question?
I think so, yeah.
And you can also do the percent sign before that. So if I did percent sign, art, percent sign, that means it's looking for anything with a class that has a name with art in it. It doesn't have to start with art. All right. So
may I ask you a question about that last slide again? Where that second to last line where it says grade in A and B, is that like saying contains A or B? I'm not sure I understand what that's doing.
where's that? So enrollments. So yeah, this is saying, hey, what enrollments contain an A or a B? Yeah.
Okay, thank you.
All right. Let's talk about inserting. So select everything. That's where we're grabbing data from the database. Insert, you can insert data into a database. So new records are inserted into a table specifying the table name, the columns, and the values you wish to insert. So for an example, insert into the students table, followed by parentheses, the columns I want to insert data into. So first name, last name, birth date. So these are the columns I'm going to be inserting into. The values I'm going to insert into first name, last name, and birth date are Michelle DuPont, 1982-02-11. And the order of these must represent or must be in the same order as the first name, last name, and birth date. So Michelle is the first value corresponds to the first value or the first column in right here. So insert into students, first name, last name, birth date. Any questions on that? We'll talk about, we'll go through some of this. So updating is a little more delicate, I'll say. So update allows you to change the values of a column. So I need to update the table. So what table I want to update? So I want to update addresses, and I can set what do I want to update in that table. So I want to update line 1 to equal 200 Church Street, as well as the column zip code to equal 60010. The very most important part of this is this where clause. So where do I want to set these values to is where the ID equals 2. So update the table. What values do I want to insert? And where do I want to insert them? Where the ID equals 2. If I don't add this where clause is, you're going to get really bad results, which is going to set this value to every single record in your database or in the addresses table. So essentially, if I don't include this where clause, I'm going to change every record in the addresses table to line 1 equals 200 Church Street and zip code 60010, which you don't want to do. So that's why I say it's delicate, because you need to ensure that you have this where clause in there. Same with delete. Delete removes matching rows from a table. So delete from addresses where ID equals 2. Make sure you have that where clause in there. And I guess that's what that last slide is for. If you fail to include the where condition, you'll affect all the rows in the table. So everyone moves to that 200 Church Street if you don't include the where clause. And if you just run delete from addresses without this where clause, it will delete all the addresses from the database. Any questions before we take a break?
Yeah, one quick question. So just about the zip code type, is that being stored as a string or an integer, and which would you do? Would you rather?
So this is stored as a string currently because it's got the quotes around it, and I would store it as a string. I would limit because a lot of people store data zip codes in different types, and some databases don't store trailing zeros. And if you store it as a string, you can add like a condition on that says, hey, only store it 5 characters long instead of just a random integer. Or I can store it 6010 dash something else.
That makes sense.
Hey, Tom, I had a question too.
Yep.
Given that you said if you don't include the ID, it could update all the rows, is there something that like companies do in order to do they not like you to use something like this, given that it could potentially cause a problem like that? I'm just curious as to like if there's like safety measures in place or anything.
Yeah, typically companies don't write raw SQL. They use an ORM that will prevent you from doing all that. But yeah, usually there's multiple checks that go along before you will even update that.
Gotcha. Thanks.
Yep.
Hi, Tom.
Yep.
So if I delete my data by mistake, is there a way I can get my data back?
No, let's just short answer is no. There might be a way. Typically big companies run back up their data quite often just in case something happens. But typically if you delete everything from addresses, it will be very difficult to get it back.
Okay, thank you.